and welcome back. In today's video, we're actually going to be building this thing. And as cool as I think this thing is, it's not actually the primary focus of the video. Well, not in the completed form at least. What I want to do today is I want to show you guys how I go about making a circuit board. Not just the machining part of it, but from idea all the way through to finished product. So I'm talking about how I figure out the logic diagrams, how I figure out the schematics, how I simulate it, how I build the PCB on the computer, and then finally, how I machine the PCB on our Bridgeport CNC 3-axis mill. So we've got a lot of stuff to cover today, so let's hop over to the bench. I'm gonna flip open the laptop and I'm gonna walk you guys through my entire process from beginning to end. So let's hop over there and get started. All right, so the first step is to figure out what on earth it is that I want to build. And for that, my go-to program is almost always Logisim. This is a fantastic free little program that allows you to simulate logic gates. And while I have only just started to scratch the surface of what this program is capable of, you can see, well, I actually have something quite complicated built in it. This is actually the logic diagram for the UE14500, the vacuum tube computer. I built it completely in Logisim first, but this took just about a year of designing and building, and I want to do something today. So I think what we're going to build is a half adder. So in our new document here, we'll put 2 buttons as our input, and we will put 2 outputs in there as well. And essentially what a half adder does is it takes the input from these 2 buttons, which are 2 1-bit inputs, adds them together and gives us a 2-bit output. Now half adders are pretty easy to build. You just need an AND gate and an exclusive OR gate in parallel. And you can see here that if operand A or operand B is on, the sum illuminates, but if both operand A and operand B are on, the carry illuminates. This is a simple half adder. However, through experience of building the vacuum tube computer, I have learned that building an exclusive OR gate is quite difficult at times. So we'll rebuild this with 1 NAND gate, an inverter, and 2 NOR gates. And this should give us a half adder in just 4 vacuum tubes, which I'm going to use the 6AU6. So we've got the logic layout for the half adder that we want to build. The next step is to figure out how exactly we're going to build those logic gates. And for this, my go-to program is TINA TI. This is a Texas Instruments distributed version of the DesignSpark TINA circuit simulation software. Now it is a piece of free software, but you do have to fill out some information on the website. You have to input your name and what you're going to use it for and a couple other things. Now this software is based on the SPICE framework. But it's probably not as good as LT Spice. But the user interface of this is infinitely better. And you can also import SPICE models. I've imported the 6AN8, which is a triode pentode combination tube. I only imported the pentode side of it. Now you can see it shows up here as a tetrode, but that's because the suppressor grid is tied to the cathode. But in my testing, I have discovered that the 6AN8 pentode here in the simulation software at the voltages that I'm running at, which is a B plus of 24 volts with a grid biasing of minus 12 volts, at those voltages, the 6AN8 pentode simulates almost identically to the 6AU6 pentode in the real world. So in the TINA TI software here, we'll build up a basic inverter. And essentially the way we do this is we tie the cathode to ground. We tie the plate to 24 volts through a 33,000 ohm plate resistor. The screen gate goes to 24 volts through a 100 ohm resistor. And then for the control grid, we have a 4.7 thousand ohm resistor that feeds into a 220,000 ohm, 220,000 ohm resistor divider that goes between our incoming input and minus 12 volts. So now that we have it set up, if we go up to the TNM menu, we can open up the digital multimeter. We'll set it to DC. It's reading off of the output directly off the plate, and you can see that it's at 24 volts, and then when we click the switch, it drops to 3.4 volts. And this is very, very close to how the 6AU6 operates. I believe the 6AU6 goes a little below 3 volts depending on the quality of the tube. I have some that don't make it to 3.5 and I have some that make it below 3.5. But this is close enough to pretty much tell me that all of these resistor values are going to work fantastically in the real world with the 6AU6 pentode. Next, we'll make a NOR gate, and essentially all we're going to do is copy over the inverter, add 2 inputs through 2 diodes. And that's it, because 2 inputs through 2 diodes is an OR gate, and then the inverter inverts it to give us a NOR gate. Finally, we'll build a NAND gate. This is built very similarly to the NOR gate. We just flip the diodes around, and then we use two 20,000 ohm resistors to minus 12 to essentially build a diode logic AND gate, and then we have the inverter to amplify and make that output out of the AND gate stronger. So now we have essentially a blueprint for the different logic gates that we need to build the half adder. All we need to do is figure out I don't know if you guys can hear that. The cows are mooing about something like crazy out there. Let's go say hi. All right, I don't know what the cows were going nuts about, but they seem to be moseying on along now. The joys of living on a big old ranch in the middle of nowhere. But anyways, getting back to the topic at hand, now we have the basic fundamental logic gates figured out for the half adder that we want to build. Now we could build this out even further and simulate the entire half adder in Tina TI, and well, that's what I've done here. But with larger circuits, like if we were to build a full adder, Tina TI starts to chug, but we know that the basic fundamental logic gates work. So all we need to do is just plug those logic gates together like Legos. Now on the occasion we have to watch out for fan out issues, but here that's not going to be a problem. So now let's move over to designing the PCB. And for this, my go-to piece of software is DesignSpark PCB. This is also a piece of free software, and well, there's a lot of different EDA software on the market. A lot of people like to use KiCad or Eagle. Personally, this is the one I like, but I think it all comes down to using whatever you're most familiar with. Now in the software here, the first thing that I like to do is I like to set my design grid up to 2.54 millimeters. This is the standardized spacing for the DIP package, but also a lot of through-hole components like this spacing. Now this means that the traces can only be at intervals of 2.54 millimeters, which doesn't particularly work for a lot of the more difficult surface mount designs. But I've discovered that on my mill, this spacing seems to work well. It gives me plenty of isolation between the traces, makes it easier to solder things without getting solder bridges, and that just seems to work the best. Now playing into that, we also have really fat traces. I'm using 1 millimeter thick trace widths here, which is a lot thicker than is usually used on PCBs. So now that we have the very basics of it set up, from here, it's just a matter of building out the circuit, one connection at a time. Now I have a custom footprint for the vacuum tube here. This is because I use a different socket than most people use. I use these little Harwin H1361 or something like that. They're just essentially 1 millimeter PCB pin headers. And it just so happens that the legs of a vacuum tube, of 7-pin and 9-pin vacuum tubes, are perfect for these. They fit perfectly into here. Now there are some caveats Because the pin headers are mounted directly into the PCB, there's no room for them to move around. So there can be some thermal stress on the pins and the glass as the tube heat cycles, and this can potentially cause the glass to fail and the tube to go to air. That is a problem that I have never run into, but I don't run my vacuum tubes on a daily basis. So we've got our footprint. We just need to put all the components in place and run all of the traces. For me, I find doing this extremely therapeutic, and I have countless PCB designs on the computer that I probably will never build just because I had an idea and I needed the therapy of building it out in person. All right, I'm getting pretty happy with this design. You may notice that anytime I needed the trace to change directions, I always went through the extra effort of adding a 90-degree arc to it, essentially making the trace actually curve to change directions. This has absolutely nothing to do with the capabilities of the mill. The mill will machine 90-degree turns with no problems whatsoever. It has everything to do with the fact that I just think it looks cool. But we have a design here that I'm pretty happy with. This is hopefully a working half adder, but we don't have any way to see the output. So I'm going to kick the cameras off, sit down and have a think about how we can see that output, maybe put a few bells and whistles on there, and we'll come back whenever we're ready to take that and set it up for the mill. All right, here's our final design, and I'm quite happy with the way this is looking. Now we just need to figure out a way to get it from this piece of software to G-code, because G-code is what our mill is going to be able to read. And well, DesignSpark or any of the EDA software won't output G-code directly, but they will output something called Gerber files. So that's what we're going to do. We're going to output manufacturing plots, and we're going to essentially aim for 3 different Gerber files. We're going to have the drill files that are for where all of the through holes are. We're going to have the isolation, which shows us where all of the traces are. And finally, we're going to have the board cutout, which is the outline cut around the outside. Once we get all those Gerber files output, we will open up a program called FlatCAM. Again, this is a piece of free software and it is excellent. This software is dedicated to reading Gerber files and turning them into G-code. So the first thing we're going to do is we're going to open up all of our Gerber files. And once we have all the Gerber files open, we will select them all and flip them on the X-axis. Because we're going to be doing single-sided PCBs, these traces are for the bottom copper. And when we were designing it in the EDA software, we were essentially looking through the top of the PCB at the bottom copper. So when we cut it, we have to make that bottom copper face up, which is going to essentially reverse everything. So we just flip it on the X-axis and then we're good to go. Now next we're going to start setting up the passes. The first thing that I like to do is the cut pass. This is the essentially the pass that cuts out the shape of the board. But I also have some mounting holes as well as the holes for the vacuum tubes themselves. And you can see that when we open up the cut pass here, it has a cut on the inside and the outside of the outline. And we don't want it to cut one or the other depending on the situation. So for the outline of the board, we don't want it to cut inside and make the board too small. And for the mounting holes, we don't want it to cut on the outside and make the mounting hole too big. So I just right-click, edit it, and delete the unnecessary cuts. Now for the isolation passes, it takes a little bit of math. I am using a 60-degree V-bit. What this has is a 0.1 millimeter tip, and then coming away from that tip, it comes out in a 60-degree V. What this means is that the deeper we cut into the board, the wider we're cutting as well. But we need to tell the software exactly how wide we're cutting for the depth that we're going to cut at. So it took a little bit of math and it came out to 0.331 millimeters. So I just punched that in as the tool diameter. I tell it how many isolation passes I want, and I personally like 3 passes. I'll combine those and we can see here's all of the isolation passes. Next, we'll set up the drilling. There's 4 different drill sizes listed here, but I'm just going to use a 0.9mm drill bit for everything. That seems to work really well for through-hole components. And finally, it's time to start making the G-code for each of these processes. We'll start with our isolation passes. Here, this is where we set it to a V-bit with a 60-degree V-tip angle, and I like a feed rate of about 320. Faster means the cut finishes faster, slower means it takes longer but is nicer. I found that 320 is a good balance between speed and clean cuts with the specific PCB I'm using. If you use different PCBs, this speed may need to change a bit. Also, our mill can only go up to about 3,000 RPM. If you're using a tabletop CNC router, some of those can go up to like 10,000 RPM, which means that your feed rate is going to need to change to match the spindle speed that you have. With all 3 of our CNC jobs set up here, you can see that everything is highlighted in blue where it's going to cut. And then all we have to do is save the G-code to a little compact flash card that our CNC machine can read. And then, well, it's just getting it actually physically set up on the machine. So let's hop out to the garage and get started on cutting this PCB out. All right, and here's the mill that we're going to use to cut out our PCB. It is a Bridgeport EZ-Trak with an Accurite mill power 3-axis CNC setup. Now the spindle motor is actually a 3-phase motor, and we only have single phase out here. So we've got this big box on the wall here that converts single phase to 3-phase. So the first thing to do is to pop in the compact flash card with our newly made G-code on it and then power the machine up. Once it has fully booted up, it's time to get our PCB mounted. I actually mount the PCB to a block of wood that is in our vise here. Now, to ensure that the surface of this wood is perfectly parallel to the spindle, I grab the biggest bit that we have and I chop off about the top 0.5 millimeter of the wood. So my 2x4 here is getting skinnier and skinnier every time I cut a PCB, but that's okay, it's a sacrificial layer. And then to mount the PCB to it, I put down 2 strips of very sticky double-sided carpet tape. This stuff is super sticky and seems to hold the PCB in place perfectly. Once my PCB is nice and firmly stuck to the carpet tape, I then grab my V-bit. This is the 0.1mm 60-degree V-bit that I use to make my isolation cuts. I put it in the appropriate sized chuck, I tighten it right on down, and then it's time to start working on zeroing out the Z-axis. And to do this, I use a 0.05mm feeler gauge. So I start by bringing the tip of the V-bit very, very close to the PCB copper surface, and I slide the feeler gauge in between the bit and the PCB surface every time I drop just a tiny little bit. And I do this until the feeler gauge will not slide through. So this means that the tip of the V-bit is right now at Z equals 0. So we go to datum, we set Z equals to 0, and there we go. We've got our Z-axis zeroed out. Next, we want to zero out the X and Y axis. I lift the Z axis up just a little bit, and then I bring the bit all the way to the front left corner. I actually bring the X equals 0, Y equals 0 point inboard just a little bit to compensate for the fact that I probably didn't get the PCB mounted perfectly straight on the board. And there we go. All of our axes are zeroed out, and it's time to start the cut. So we load up the program, and this actually takes quite a long time. This program has a little over 50,000 steps, but once it's all loaded up, we hit go, and then I make sure that the first cuts look like they're doing good. If I got my Z-axis wrong, it either won't cut deep enough or it'll cut too deep, and I've messed up enough times where I've been able to recognize what that looks like pretty quickly. So it looks like it's cutting pretty well here, but I want to give it just a little bit of time to double check. So I'm going to hop in the other room and maybe play a game on the Merry Widow. And once I've finished the game on the Merry Widow, I'll run back out, make sure it's cutting well, and yeah, there we go. It is still indeed cutting well. But I do want to triple check it here again in about another 5 minutes. So I'm going to hop back into the other room and play a game on the Elton John pinball machine as well. And back on the mill, it looks like it is progressing just fine. We're only at about step 10,000 out of 50,000. So this is now the hardest part of the entire process because I just am gonna head inside and wait 40 minutes. After about 40 to 45 minutes, it looks like our isolation cut has finished. That means it's time for a tool change. And the next tool is a 0.9 millimeter drill bit. Now I need to get the tip of the drill bit perfectly to Z equals 0. And in order to do this, I put the bit in the chuck and I get it just hand tight. Then I lower the Z axis until the DRO reads 0. This actually pushes the bit into the chuck. But once the DRO is reading 0, this means that the tip of the drill bit is sitting perfectly at Z equals 0. So then I just tighten down the chuck, then we need to load up the next program, hit go, and double check that everything is drilling correctly, and it looks like it is, so we're just gonna let it run. Drilling often takes about 5 minutes, and once it's finished drilling, it's time for our final tool change, which is to this 1.5 millimeter end mill bit. Now again, I get the Z equals to 0 using the same process that I did for the drill bit. Once it all looks good, I hit go, make sure that it's cutting well, and then sit back and let it do its thing for another 10 minutes or so. And there we go, we have completely cut out a new PCB. I just give it a quick cleanup with a soft wire brush, and here is the finished result. It looks absolutely stunning. I'm really happy with the way that this one turned out. So this is a fantastic way to design a PCB in the morning, cut it, and build it in the afternoon. And speaking of building it, that's our next step. So I'm gonna go ahead and solder this one up, and then I'll show you guys what it looks like when it's finished. All right, here's the finished product, and I'm pretty happy with how it turned out for just a thing that we were building for fun. I love the way that this little 7-segment VFD has been held in place with all of the leads on the front here kind of bent over, and then the tip over here held in place with a single wire. And you can see it's displaying 0. If I push one of the buttons, we get to 1. If I push the other button, we get to 1. And if I push both buttons, we go to 2. Look at that. So that's our half adder. 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 1 is 2. So there we go, we managed to build a half adder out of 4 vacuum tubes and a single display VFD over here, and I'm really happy with how it turned out. Though the finished product, as cool as I think it is, was not the main point of today's video. I just wanted to give you guys a closer, in-depth look as to how I go about building something from idea to completion. So today's video was a little on the long side, but I hope you guys enjoyed it, and I hope you learned a bit about my entire construction process. So I want to thank you guys so much for watching, and I hope to see you next time.